Hello. Now we're going to continue our work in algebra, and we are going to be looking at an idea called proof by induction. And today we're going to be doing a series version of a proof by induction. So I'm going to start off very briefly by reminding ourselves of what a series is. A series is where we add up a whole bunch of terms. So this comes from our sequences and series, or the patterns part of our course. And to link it in more explicitly there, we're going to have our Tn, the equation that gives us the terms in our series, is 4n minus 3, and this term over here is the sum of terms, so it would be S of n when we would be doing our sequences and series work. So this is to link it in. This is a series in the same way as our sequences and series chapter is going to deal with, in the same way as our patterns chapter is going to deal with. So that's what we've got going on here, and we want to prove that the sum of these terms is equal to this equation here, is equal to S of n, the sum of the terms formula. And to do that, we are going to use proof by induction. There are several different types of proof by induction. There is a series one, which we're doing today. There's a divisibility one, which we'll be doing next. And then finally, there's an inequality version of proof by induction. And we'll go through all of them in turn. But now that I've introduced what our series is, what we want to prove, I'm going to briefly talk about the method for proving it in the abstract, and then we're going to get into the question and put it into practice to make it clearer. So proof by induction is a formal proof. There is a step 1, a step 2, a step 3, a step 4, and you literally label that on the exam. So these questions are very rigorously structured. They look exactly the same all the time in terms of structure. Part 1, or step 1, will always be show that our particular pattern, in this case this series, is equal to this equation. So show that this pattern is true for n is equal to 1, usually. There are some times when you will be given a restriction where n must be greater than 2 or 3, but in general, you will be doing your first step as n is equal to 1. That is, in this formula here, I will be subbing in 1 for n. So I will be looking for the first term in my series is equal to my equation here. Part 2, I'm going to say that I assume that this pattern holds. So I am assuming, I'm not proving, I am assuming that this pattern holds, that this equation is true for a particular value of n. And the particular value of n we choose is usually called k. You don't have to call it k, but that's the tradition. Now k is just a variable, just like x or y that we've been using for years. It's just a number. So k could, in principle, be 2, or k could be 1,025,000. K is just some number, but we're not specifying what number. So it's a particular number in our series, a particular term in our series. Part 3 is where most of the maths happens. It's show if n is equal to k is true, that is, if what we've assumed is true, therefore the next term would also be true. The n equals k plus 1th term would be true. This will make more sense when we've gone through a question, but the basic idea of it in English is, can we show that if our relationship is true for a particular value of n, can we show that it is automatically true for the next value of n? So if it was true for n is equal to 1, would it also automatically be true for n is equal to 2? That's what we're trying to demonstrate. And finally, is the part 4 is just a wrapping up of what we've been doing so far, but we have to put it in. This is where the last block of marks in our exam comes in, is stating what we've done and why it mattered. And it's what I just said pretty much. If we have shown that our relationship holds for a particular value of n, usually n is equal to 1, and we have shown that our relationship holds for a particular value of n, then it must also hold for the next value of n, then we've effectively shown that it must hold for all values of n. Because if our relationship holds for n is equal to 1, and we know it always holds for the next term, that means it holds for n is equal to 2. But if it's true for n is equal to 2, then our relationship must also hold for the next term, which would be n is equal to 3. And this pattern just continues. Therefore, we have shown that our relationship must be true for all values of n. But this is all very abstract. The last thing I want to touch on in terms of structure, and I'm going to come back to it at the end, is if we have a look at our marking scheme, proof by induction is a very fiddly question, and they take that into account in the exam marking scheme. So even though these questions are often quite unpleasant, it's possible to pretty much get 50% in them with almost no work. And that's what we're always going to get the first 50% of marks in a proof by induction question by doing these two steps plus writing down what n is equal to k plus 1 will look like. Again, that'll make more sense in a few minutes. So if I want to prove this relationship here, I have my series of terms adding up, and this is the tnth term. So this would be term 1, term 2, term 3, term 4. And I'm adding them all up. So this is when n is 1, n is 2, n is 3, n is 4, on up to whenever we stop, whatever the value of n is. And I have my n's on this side of my equality as well. So part 1 is going to be show that this relationship holds for n is equal to 1. So set n equal to 1. So I'm looking for the first term. So on the left hand side, I'm just going to get 1 because that's the first term in my series, and I need to sub 1 in here. But for completeness, I'm going to sub into the formula here. So I'm going to show that 4 on 1 minus 3, this will be the first term. I know it's going to work out to 1, is going to equal 1 all over 4 on 1 minus 2. This side is equal to, write it out here, we have 1 is equal to a half on 2, 1 is equal to 1. Now that's true, 1 is equal to 1. So that job is done. Next step, I'm going to state that I'm going to assume that my relationship is true for n is equal to k. And again, k is just some number. I'm going to assume that it's true. I tend to write tick for true. So assume that that's true. Let's write down what that would mean. It would mean if we started off with 1 plus 5 plus up to our final term, this case we're subbing in k for n, k all over 2, 4k minus 2. I'm assuming that that relationship is true. So for a particular value of n, which we're calling k, we're assuming that the relationship does hold. We haven't proved it, we're just assuming it. Part 3, this is where the real maths happens. I want to show that this is the n equals kth term of my series. I want to show that if n equals k is true, then n equals k plus 1 is also true. The next term must also be true. So what does that look like? Well, n equals k plus 1 would be 1 plus 5 plus so on up to 4k minus 3. That's the kth term plus the next term. If I added on another term, I'd be on the k plus 1th term. So anywhere there was a k, I'm going to put her in k plus 1 is equal to, anywhere there was a k, I'm going to put k plus 1. Now, just to highlight at this point, I have 50% of the marks for the question. I've done almost no maths. So we're always going to do these questions and get to this point where we're writing down the k plus 1th term. Even if we don't know how to continue from there, this is 50% of a question on a Leaving Cert exam paper, and we've done almost no work if we can remember these steps. Now, we're trying to go for 100% of the marks in the question, so we continue. This is what the left-hand side of my equation needs to look like. This is the right-hand side. I need the left-hand side to look like this. I need the right-hand side to look like this. But the right-hand side at the moment is a big mess. This is at least a series. I know what that looks like. But this is a mess. I want to tidy this up so I know what my right-hand side needs to end up looking like. So I'm going to take my right-hand side and I'm going to simplify it down so I'm able to identify it more easily. So I have k plus 1 all over 2. On multiplying this in, I get 4k plus 4 minus 2. I have k plus 1 all over 2 on 4k plus 2. I recognize that I can divide both of these terms by 2. So I get k plus 1 on 2k plus 1. Multiplying out those brackets, I get 2k squared plus 3k plus 1. I'm skipping over a line there, but we should be able to multiply out brackets. So this is what I want my right-hand side of my equation to look like. That's my aim. Now let's go to what we've assumed to be true. So this is what we're going to start with in a series type equation. We're going to start with what we assumed to be true. So n equals k is what we assumed to be true, and it's going to be a starting point. And this gets very wide, so make sure you leave yourself lots of space on your answer sheets for this part because it necessarily takes up quite a lot of space. I start out with my kth term that I have assumed is true. I'm going to write it out. So what I've started with then is I have my kth term. This is n equals k, and in my blue writing what I've done is add on the k plus 1th term. Why did I do that? Because I look at my left-hand side, and the only difference between the kth term and the k plus 1th term is to add on the k plus 1th term onto it. So my left-hand side is now perfect. My left-hand side is now exactly the way I want it to be. I need to rearrange this business here to see if I can make it look like this quadratic. And if I can, my job is done. So I'm going to multiply in this bracket here, so I get 2k squared minus k. So this is the right-hand side, and I'm trying to make it look like this quadratic. Plus 4k plus 4 minus 3. And if I tidy that up, I get 2k squared plus 3k plus 1. Now that is the same as my aim. So I now have my right-hand side and left-hand side the same. What I did was I started with what I assumed to be true. I added on the k plus 1th term to both sides so that the left-hand side would look like I wanted it to. And then when I tidied up the right-hand side, it ended up looking the way I needed it to. This means that my pattern holds. If my pattern holds for n is equal to k, I've shown that the pattern also holds for n is equal to k plus 1, which was my aim. Now I'm going to write out the last stage. So our last statement is simply saying that we understood what we just did. As n is equal to k plus 1 is true if n is equal to k is true, and n is equal to 1 is true, therefore the next term, n equals k plus 1, would be n is equal to 2 is true, and then the next term must also be true, n is equal to 3 must be true, then 4 must be true, then 5 must be true. So we find that we have shown that our relationship is going to hold for all values of n. Now, I am aware that this is fiddly and a little bit odd looking. If we can get our heads around it, fantastic. But what absolutely everyone must take away from this is that there is almost no maths involved or nothing terribly tricky involved. It's just a bit of memory work to get us up to this point here. And that is 50% of the marks for this question. So everyone is getting 50% or more in a proof by induction question. So those are our steps for our series.